Hi, yeah, my name is Sarah Kane, and primarily my research is in galactic archaeology, which means that I use stars to understand the history of our own Milky Way galaxy. But I'm actually not going to talk about that today. Instead, I'm going to talk about what I call my side gig interest in astronomy, which is data sonification. Now, it'd be something of an understatement to say that sonification in astronomy has become kind of popular recently. Here's an article about it from Scientific American. Here's one from the MIT Technology Review. Sorry, I'm an American, so a little bit of an American bias here. Here's one from Nature. So it's everywhere. Astronomers recently have been really liking sonification. But what is this sonification thing? Well, in the simplest terms, sonification is the representation of data using sound. Now, this is directly analogous to data visualization, which is where we represent data using some visual medium. And we do this all the time. Think of your line graphs, your bar charts, your pie charts, your histograms, the list goes on and on. We are always representing data through visual media. This is a representation of the data. The data doesn't actually look like a bar chart, but we explain, we describe the data through this visual medium. Now, much as this data doesn't actually look like the data visualization, sonifications are not what the data actually sounds like. So what are sonifications not? They're not sounds from nature, like bird songs. They're also not typically words. So if I have some astronomy data and stand here and tell you about it, that's really cool, but that's not typically what we'd consider sonification. Now, in a few minutes, I'm going to play you a couple of sonifications, which will hopefully help give you a more concrete understanding of what I'm talking about. But first, I want to break into why would we want to sonify data in the first place? Why would we want a sound representation of data when we have, as I've mentioned, 1,000,001 data visualization tools? Well, there are a couple of reasons we might want to do it. First, there are some groups that are traditionally excluded from data visualizations. These are people with visual impairments like myself. This makes accessing data that is represented through visualization immensely difficult. So by sonifying or representing as sound this data instead, we make it accessible to a whole new group of people that otherwise couldn't use it. There are also some physical reasons that we could expect both blind and low vision and fully sighted people to enjoy and find great usefulness in sonifications. One of these reasons is that our ears are actually much more sensitive to small changes than our eyes are. You're much more likely to notice a small change in pitch than your eyes are to notice a small change in brightness. Also, our ears have what I would say is a faster refresh rate than our eyes. Think of like frames per second on a video. Your eyes just don't see new images quite as quickly as your ears hear new sounds. And the fact that sonification is useful is evidenced by the fact that we've been using it for a long time. This is not some newfangled contraption that we've just come up with. One of the most famous examples of a sonification is this thing, a Geiger counter. Maybe some of you have heard of it? Yeah, maybe? So Geiger counters measure how much radiation, ionizing radiation, the dangerous stuff, is coming off of an object and will make clicking noises to tell us how much radiation there is. This is not an alternative to a visualization. This is actually just how people do it. We've been using sonifications for a long time. And this all comes back to an idea that I'm always badgering on about called universal design, which is that when you make something, an object, a tool, a space accessible for disabled people, you're actually just making it better for everyone. How many people here use a phone or a computer and sometimes like to use dark mode? Like the slide where you have light text on a dark background. Anyone? Dark mode? Yeah, I can't tell, but I'm assuming some of you are raising your hands because everyone uses it, Well, that was actually originally an accessibility tool. I like dark mode. I read all my text in dark mode. It's easier for me because of my disability, but lots of sighted people like it too, and so now it's everywhere. That's universal design at play. All right, so now we've given some of the theory about why we want to sonify things. We have at least like a rough background of what sonification is. Enough of me talking. Let's actually listen to some pretty sounds that represent astronomy data. In particular, we're going to be listening to sonifications from NASA's A Universe of Sound project. These are a repository of sonifications from NASA telescopes. In particular, here we'll be listening to ones from the Chandra X-ray telescope. The project is led by Dr. Kim Arcand, also including Dr. Matt Russo and Dr. Andrew Santaguida, who all work together to make this project. And I'll be playing for you a couple of sonifications from this library. Now we're going to start by listening to a sonification of the galactic center. And this sonification is accompanied by some text explaining how they translated the data into sound. So I'll read that for you now. Explore the center of our very own Milky Way galaxy. The translation begins on the left side of the image and moves to the right. Sorry about that. And moves to the right, with the sounds representing the position and brightness of the sources. The light of objects located towards the top of the... Oh, sorry, guys. This is a moment where I really wish I knew Braille, because I'd be a little bit more competent here. With the sounds representing the position and brightness of the sources. The light of objects located towards the top of the image are heard as higher pitches, while the intensity of the light controls the volume. Stars and compact sources are converted to individual notes, while extended clouds of gas and dust produce an evolving drone. The crescendo happens when we reach the bright region in the lower right of the image. This is where the 4 million solar mass supermassive black hole at the center of our galaxy, which we call Sagittarius A star, resides, and when the clouds of gas and dust are the brightest. All right, let's give it a listen. Let's hopefully give it a listen. Oh, it was too much to hope this would work easily, wasn't it? Sagittarius A star resides, and when the clouds of gas are the brightest. All right, let's give it a listen. Let's hopefully give it a listen. Oh, it was too much to hope this would work easily, wasn't it? Sagittarius A star resides, and when the clouds of gas are the brightest. Okay, all right. Catherine, if you're in here, can you go about that? We'll just give that a second. Okay, all right. Catherine, if you're in here, can you go about that? Okay. I don't know. A second.
I'm gonna get Matt.
Okay. Just a moment. Catherine, if you're in here, can you go about that? I don't know.
What's wrong?
We have a sound loop.
Sorry?
We have a sound loop with a YouTube video going.
Oh.
I'm gonna get Matt.
I don't understand what's happening. So where's the sound coming from?
It's like
So if you go to a different slide.
we have a sound loop.
Sorry?
We have a sound loop with a YouTube video going.
Man, people were complaining about no sound last week. Now there's too much sound. It was like,
Oh my god.
there's no sound. I don't know where the sound. Where's the sound?
Are you on the live stream of?
So if you are you watching your own live stream? By any chance?
Oh my god. Am I? I'm just gonna. Let me just.
There's no sound coming out here.
Oh my gosh, it is my own.
You're watching your own live stream. Okay, we have found the problem. Okay.
I didn't anticipate that one.
Okay, are you good?
Yep, I'm just gonna like assemble myself again. Yeah, we're.
It's fine. You're among friends here.
Oh my goodness.
Okay.
All right.
So, are you happy to?
Wow, that was. Okay.
If it makes you feel better, it's been the best lecture ever.
I suppose this has made it memorable, hasn't it? Sorry, if you're seeing it magnified, that's just how I see my screen. But it should be back to normal now.
Okay.
Okay.
Leave it to us.
Everyone cross your fingers for me? Yeah? All right, this is the moment where it all went wrong. All right, cool. Hopefully that was worth the wait, yeah? All right. Ooh, okay. So that sounded very pretty, at least hopefully, I hope you thought so. It's a lot of work to get it up there. But actually what was happening there was they were sonifying the data that was represented both in that image in the video and in the sound through a relatively well-established sonification technique, one that we call parameter mapping. Now in parameter mapping, what we do is we take certain aspects of, of the original data, for instance, the color or the brightness of an object, and we map each of those aspects of the data to a different parameter in the sound, whether that's the pitch or the volume or a different instrument. And there are a lot of different aspects of the sound, different parameters in the sound that we can map to. This means that we can represent very high dimensional data in our sonifications, higher than we can often do in visualizations. What do I mean by this? Think again about our line graph. It has what we would say are two dimensions, X and Y, the horizontal and vertical axis. If you add maybe some color labeling to this line chart, you can maybe have a third dimension, but in a visualization, it's really hard to represent much more than that. But our data can have many dimensions. Say you have time, X, Y, and Z. Well, suddenly that's 4 dimensions. I mean, that's kind of our own universe. That's really hard to plot visually. But there are a lot of parameters in sound we can map to, and that makes sonification really powerful for representing complex high-dimensional data. Now, that all might have sounded a little bit abstract, so what we're going to do is we're going to revisit the description of this sonification, the one that's provided by a universe of sound, and we're going to go through and break it down into the different parameter mappings that this team is using. So let's go through it together. Explore the center of our very own Milky Way galaxy. The translation begins on the left side of the image and moves to the right. Well, we found our first parameter mapping in this sentence. What's happening? Well, the position along the horizontal axis of the image, so moving from left to right, is being mapped to time. You know that the later time you are in the sonification, the further to the right in the image you have moved. All right, our first parameter mapping. Then as we continue with the sounds representing the position and brightness of the sources. The light of objects located towards the top of the image are heard as higher pitches. Another parameter mapping. Here we're mapping the vertical axis, so now the height direction, to the pitch of the sound. Higher pitches, higher in the image. While the intensity of the light controls the volume. Wow, we don't have to move very far to get our next parameter mapping. In this case, how bright the object is, the intensity of the light, maps the volume. So brighter things in the image are going to be represented as louder sounds. Stars and compact sources are converted to individual notes, while extended clouds of gas and dust produce an evolving drone. All right, there's one last bit where we have the size of an object in the image mapped to the note duration or the sound duration. So you know that if you hear a longer sound, it's representing a larger object within the data. All right, so here's our summary of how this team has mapped the data from the galactic center, from the Chandra telescope, to sound, how they've sonified it. This is almost our exact recipe for what they've done. We know that along the horizontal axis, they've mapped to time within the sonification. Vertical axis of the data is mapped to the pitch of the sonification. How bright an object is mapped to the volume. And then how long a note is represents how large the object that sound is representing. All right, try to keep this all in your mind because now we're going to listen to that sonification one last time and see, hopefully, that maybe it'll be a little more interpretable. All right, so what do you think? Did you find the sonification easier to interpret now? What do you think? You can raise your hand. Again, I can't see it, but you know. Hopefully some of you raised your hand, but even if you didn't, that's okay. Because actually, we spend a lot of time learning to understand and interpret data visualizations, graphs and charts. This is a big part of education for children in school. For instance, back in the US, on a big standardized test we have called the ACT, we take it to get into university. A whole section of it that we call the science section is basically reading graphs, and people study for months to take this. We think of those line charts and bar charts as very intuitive and a natural way to represent the data. But actually, we were just taught really rigorously from a relatively young age to interpret them. So there's no reason to expect that we shouldn't need the same level of education to interpret sonifications. So hopefully it was a little more interpretable once we went through the parameter mapping, but you know, I understand that it might, in fact, I would expect it to take more time for it to completely make sense. All right, but let's not totally give up there. I mean, it'll be a little bit of a sad presentation if we only listen to one pretty sonification. So we'll listen to one more, again, from the Universe of Sound project. This one is a sonification of an object we call Cassiopeia A. Cassiopeia A is a supernova remnant, which means that a large star at the end of its life exploded and blew its outer layers all around it in a massive explosion that you can see like across the universe. Now, at the core of this explosion is the core of the star, which didn't explode out. In this case, it remained as something we call a neutron star, this unimaginably dense object. And they're really cool, but I'm not going to get into that right now because we're here for the sounds. So once again, the Universe of Sound team has for us a description of how they sonified this. And again, we'll break it down into the parameter mappings that they used. This sonified piece is the remnants of a supernova called Cassiopeia A, or Cas A. In Cas A, the sounds are mapped to 4 elements in the debris from the exploded star, as well as to other high-energy data. The distribution of silicon, sulfur, calcium, and iron are revealed moving out from the center of the remnant, starting from the location of the neutron star, that's right in the center, in 4 different directions, with intensity, again, controlling volume. All right, so if we break this down, there are roughly 3 parameter mappings here. It's not stated particularly explicitly, but each of the elements here is mapped to a different sound, like a different instrument within the sonification. So you'll hear these 4 elements, silicon, calcium, iron, sulfur, as different instruments. They're also provided separately, so we'll listen to them as a composite and then also separately. We also are mapping, in this case, time within the sonification to distance moving outward from the center. So we're not panning from left to right, we're moving from the center out. And then finally, just like in the previous sonification of the galactic center, here we have the intensity, or how bright the spot is, represented by the volume. All right. That one's a little shorter. But so that was the composite of all four of those elements represented as sound put together. Let's listen to one of them. This one's sulfur, sonified, so represented as sound by itself. And here you'll see it moving in, I suppose if you can see, there should be little dots tracking the path we're sonifying across, but you'll also hear it tracking 4 paths out from the center. Cool. If you guys are okay sitting with one more, we'll listen to another element, just so you can sort of compare what the two sonifications sound like for these different elements. All right, apparently we have a comedy show going. I feel like after that mistake, I'll sort of be laughing at myself for that one for a while. All right, so hopefully you enjoyed listening to those. Hopefully you at least found them pretty to listen to. But one of the things I get from people most often is, well, they're pretty, but do they really tell us that much? I mean, it's not what the data actually sounds like. You have the picture, you know, that's what the data actually looks like. Except it's not. This is not a photo of Cassiopeia A. How's that possible? Why? Well, because Chandra, the telescope that took this data, observes in the X-ray. And our eyes cannot see the super high energy light that makes up X-rays. This is not a picture of Cassiopeia A. This is a representation, a visualization of the data from Cassiopeia A that was taken by Chandra. And in this case, the colors, and you'll even find a description of this on Chandra's website accompanying this picture, this visualization. In this case, the colors, that blue, that yellow, they were mapped to the different elements in the same way the different sounds in the sonification were mapped to different elements. And this isn't unique to Chandra. No, too far. Maybe some of you have seen this picture. It's a really famous one from the James Webb Space Telescope. It was one of the first images they released. It shows, you know, these clouds of star-forming gas. It's in these beautiful blues and oranges. It's gorgeous. Except, as I just spoiled by accident, this isn't a picture exactly either, because the James Webb Space Telescope observes in the infrared, which is lower energy light than our eyes are capable of seeing. Again, in this case, the infrared light, the actual data that was taken by the James Webb Space Telescope, was stitched together meticulously. Colors were chosen both for scientific accuracy and for aesthetic, artistic purposes to make this image that you see here. a representation of the data, hopefully one that tells you about space, that gives you really valuable information. But this isn't actually what the data looks like. In fact, most of the electromagnetic spectrum, so most of the light out there, not just I am blind to, but all of the rest of you are too. In fact, only a really narrow slice of light of the EM spectrum is visible to human eyes, even ones that work properly. And so much of the universe out there is invisible to us. And that's not even getting started on the fact that we're starting to observe the universe with, say, gravitational waves, these ripples in space-time that aren't light at all. And so that's why, in the title of this talk, I call this a little tongue-in-cheek, the unseen universe. Because it's not just unseen to me, it's literally unseeable to the human eye, which makes astronomy in particular well-suited. In fact, it demands the use of data representations. Traditionally, we do it with visualization, but there's really no reason we can't do it with sound, with sonification as well. All right, so hopefully now I've played you some pretty sonifications. We have an idea of what sonification is and how it might work. And also we have some motivation for why we'd want to use it in the first place, and in astronomy in particular. So, bring it all together. How do both sighted and blind low vision, which you'll hear me often refer to as BLV, because blind low vision is long to say, people feel about sonifications of astronomy data? Now, what Kim Arkand and I and some collaborators did was we played those two sonifications that you heard, along with a third sonification that I didn't play for you today, for an audience, a virtual audience via an online form, of both sighted and blind low vision people, and asked them to respond to some prompts about the sonifications that we heard. For instance, after listening to that galactic center sonification that you guys heard, we asked them to say, on a scale from 1 to 5, say how much you agreed with this prompt. I enjoyed the experience. So 5 would be they enjoyed it the most, and 1 would be they didn't like it very much. And if we look at this histogram of responses, hopefully it's not, sorry, I know it's a lot going on there, but hopefully, so we have here in blue the sighted group, and then in the sort of transparent black hashed histogram, the blind low vision group, you have the frequency of responses. So how often people answered 5 or 4 or 3 or 2 or 1. And what we'll see is that across both groups, so among both the sighted and blind low vision folks, we see that 5 and 4 are by far the most common answer. This is a good sign. This means that people generally reported enjoying the sonification of the galactic center. We also notice a strong similarity between the sighted and blind low vision group, which means that you don't have to not be able to see the visualization to also enjoy the sonification. We also provided some other prompts to respond to. So for instance, after listening to all the sonifications in our survey, we asked participants to rate how much they agreed with this statement, again, on that same scale of 1 to 5, with 5 being the most agreement. After listening to these data sonifications, I'm interested in learning more about the universe. Here's another one of these histograms. Again, the sighted responses in blue, and the blind low vision group's responses in the black sort of transparent hashing. Whoops, I'm doing this a bunch. So we see again that 4 and 5 are still the most common responses. So both the blind low vision and sighted groups report generally being more interested to learn about the universe after hearing these sonifications from the universe of sound. But as compared to the sighted group, the blind low vision participants reported being even more interested in learning about the universe. And they reported being more interested to a statistically significant extent, which means that the blind low vision group was even more inspired to keep learning than their sighted counterparts. We theorize that this might have to do with the fact that these sonifications, as I mentioned at the beginning, are opening up astronomy to groups that have historically been excluded by the use of primarily visual media. So our key takeaways, both blind low vision and sighted people report benefiting and enjoying sonifications of astronomy data. But we notice that sometimes the blind and low vision group reports being even more inspired by the sonification than their sighted peers. Now, I'd like to leave you with that final takeaway, that we see that there is immense upcoming value in sonification, and I hope you'll be interested in learning more about it. And so I'm leaving you here with some additional resources. First, I encourage you to check out the Universe of Sound website. They have a lot more sonifications to check out if you want to keep listening. The Space Telescope Science Institute, these are the people who run the James Webb and the Hubble telescopes. They had a Day of Accessibility conference, and all the talks are online, including an excellent talk by Dr. Scott Fleming about another sonification tool called Astronify. I'm a big fan of Astronify, so I recommend checking that out. And then I would be remiss if I didn't recommend Dr. Wanda Diaz-Merced's TED Talk. She is a blind astronomer, and she talks about sonification in this talk. And finally, a little bit of a shameless self-promotion. I and a blind programming instructor are teaching a non-visual Python data tutorial series. Now, most of these tutorials are designed to be accessible to blind and low vision folks because most programming resources and instruction isn't accessible, but we have plenty of sighted people following along. And in the next two tutorials, so this upcoming Tuesday and the Tuesday after, we will be teaching how, well, actually, I will be teaching how to make sonifications of your data. So if you want to learn to do this, we encourage you to tune in. It's all virtual. It's in the evenings UK time because Patrick's back in the US, so you know, gotta work with that. And you'll find the QR code, which you can scan to the website for these tutorials right here. It's not too late to register. I'd love to see you there. All right.
Such fascinating stuff, amazing. I see lots of people taking photos of the QR code. Do we have any questions for Sarah? Yes, at the front.
Maybe a shorter, easier to explain example, but have there been any instances where sonifications contradicted something you knew from visualizations?
Ooh, that's a great question. I can't think of any off the top of my head. I can't think of any at the moment. I think there are still some things that we not exclusively, but generally only represent via sonification. So for instance, Geiger counters are one. But I think sonification is still in relatively early stages of being used for research. I would say, actually, probably the best person that unfortunately isn't here to ask would probably be Wanda Diaz-Merced, who might actually have an answer to that one, but I don't, unfortunately.
Okay, thank you.
Yes, near the back.
The universe, I noticed that the universe is more, you can hear it, but it's very loud when it's more bright. And I think it's something to do with the light energy, because isn't the energy that, like the color, isn't it like the source of the sound? So the more brightness it has, the bigger it can, like the louder it can get.
That's a really cool idea, except for the fact that we need to remember that those sounds we heard aren't actually what that light sounds like. It's just how we chose to represent it. And so yes, it was louder when the objects looked brighter, when we got brighter data from those objects. That's true. That's actually a choice that the people making those pretty sounds made. They could have chosen to make the brighter things represented by softer sounds. Might have been a sort of unintuitive, weird choice to think about, but they could have done it because not actually what the data sounds like, it's just how we choose to make it sound so we can interpret it.
Yes, please.
Is there a sort of agreed, consistent approach to mapping like data in that way, so that, you know, or do you have to kind of rely on a key, like the text that you explain each time?
Yeah, that's an excellent question. So the answer is no, and this is sometimes described as the problem of standardization. Because sonification is in relatively new stages, we don't have these standardized mappings. There are some ways that are more frequently used, for instance, having the horizontal axis mapped to time and the vertical axis mapped to pitch. That's used pretty frequently, but there's no standardization, which does require us to explain sonifications. However, I would argue that often we have to explain visualizations too. For instance, I would guess that many of you would have never known that that representation of Cassiopeia A had the colors in the picture mapped to different elements, that those weren't actually the picture of what that thing looked like unless I told you. So it's a very similar case of we often do need an explanation of how data representations are representing the data. Even in really technical scientific papers, you'll get these long captions telling you, this is what this figure shows and this is how we're showing it, you know, so it's not uncommon to need this explanation to interpret a data representation. But yes, we do still have this problem of standardization in sonification.
Yes, please.
Has psychoacoustics been explored in terms of when human hearing can hear finer differences in intensity, frequency, or phase differences in spectral audio?
Yeah, so I do know that most sonification projects do involve people with expertise in either psychology or acoustics or a mix of the two. I'll admit that that's not my expertise. I think often sonifications are designed with these sort of aspects of human hearing in mind. That's certainly not my background, so I can't say too much on it with authority beyond the fact that I know that often our ears are more sensitive to changes than our eyes.
Okay, I'm going for the last question here. Please.
Some time ago, I remember sonification of two black holes meeting, or gravitational waves that were produced. Can you talk a little bit about that?
Yeah, so this is a really cool example of a sonification because in this case, we're not mapping light at all to sound. In this case, they're mapping the wave form. So the wave, gravitational waves are literally waves in space, ripples in space. And in this case, they were mapping the amplitude of that ripple in space to different aspects of the sound. And this is, I think, really cool because this is a type of data that there's no way you could ever see, right? You can never see ripples in space. It'd be really weird. It'd be a little freaky, honestly. But we can represent them either as, you know, some line on a chart, like amplitude versus time of this gravitational wave, or as, for instance, the amplitude or, you know, say the pitch of the gravitational wave via sound. And it kind of makes sense to do that because sound is a wave, gravitational waves are waves. So kind of is, in my opinion, a sort of intuitive mapping. I think they often call this a chirp, those gravitational wave chirps. Yeah, it was really fun to see that everywhere. That was, you know, a wide popularization of sonification.
Okay, amazing. I think people are wanting the tea and biscuits. So yes, there's going to be a short break followed by a planetarium show update about the Artemis mission. Can we thank our speaker again?